the way to make the computer do something was so low friction. It was incredible. And that got me hooked. And today, there is nothing like that.
It would be so nice if bills like that were passed in Congress were presented as Git diffs.
A large part of the design of the language turned into what can I slip into the language? How can I fit it in a way that it adds creative possibilities and interesting musical ideas, but also doesn't interfere or make hard teach the basic computer science.
Welcome back. Today, I've actually been connected with Sam Aaron. Jose Valim is a mutual friend of ours, and he was like, you got to have Sam on to talk about Sonic Pi. So here we are. I'm super excited. Sam, welcome to the podcast.
Hey, it's lovely to be here.
Yeah, absolutely. Cool. Well, so Sonic Pi, when Jose first introduced you, I was like, Sonic Pi, and for some reason, my head went straight to like, I've heard of this project called Pi-hole that I actually don't know a whole ton about, and it made me think Raspberry Pi, and then I started digging in. It seems to have a whole lot less to do with Raspberry Pi than I initially thought. Is there any like connection that Sonic Pi has to Raspberry Pi, or is it totally
yeah, 100% actually.
Oh, okay.
I was a researcher at the University of Cambridge the same year that the Raspberry Pi span out, and it caused all sorts of chaos because it was obviously incredibly successful. But back then, they had a charitable mission, which was to teach children how to code with this little computer. And they were struggling a bit because a lot of the educational software that was designed for kids those days was actually pushing more towards the web and had lots of web implementations. But of course, that original Raspberry Pi was really low powered. And if you tried to open up a browser, it was super sluggish. If you opened up YouTube, good luck. So actually, there was a hole for software that ran on Linux that was free and open source, but also ran under the constraints of the hardware limitations of the original Raspberry Pi. And so when they realized that, there was a small bit of money that went around the university to see if anyone could possibly build a piece of software that could help kids learn how to code that specifically targeted that first original Raspberry Pi 1. And I got that project, and that's why Sonic Pi started. So Sonic Pi the Pi is from Raspberry Pi, and the Sonic is because it's audio, and I was taking my ideas previously building audio software and then figuring out what could I actually fit into this little Raspberry Pi in a way that's packaged so that teachers could use it to teach computer science in schools. So yeah, the Pi comes from Raspberry Pi. It was one of the first original Raspberry Pi funded projects. It shipped on the original Raspberry Pi for many, many, many years, and so they had a tight correlation. But of course now it runs on Windows, it runs on Mac, and so it's sort of freed from the constraints of just specifically the Pi.
Yeah. Okay. That's really cool to understand the origin story, because obviously I'm like browsing around the web page. I poked around the GitHub, listening to all the sound samples, and I was like, this seems very decoupled, but it makes sense that the original version. So it's not necessarily that like it needed to run on the Raspberry Pi. It's more like it was designed to have low resource usage such that it could run on the Raspberry Pi.
Yeah. I mean, the funding was specifically to build a piece of software that ran on the Raspberry Pi. It made sense to me doing that if this was to be successful, it would make complete sense to make sure it ran on as many operating systems as possible. So I designed the architecture such that it could be cross-platform. But that didn't actually come for a couple of years later. The first version was actually not just designed for the Raspberry Pi, but actually coded on the Raspberry Pi, because my knowledge of minimum knowledge of building systems which are very constraint bound is it's very tricky to take a system and to try and reduce the fat. It's much easier, I think, to build it within the constraints of the environment and grow it, and then you immediately reach those constraints and you push back straight away rather than towards the end. And I think that's much easier to then have something which actually at the end works well on that target platform, rather than trying to somehow squeeze it in and failing.
Yeah. That sounds really cool. Okay, so we're going to get into some of the implementation stuff that I think is really interesting. It's part of the reason that Jose connected me with you, because I know you're doing some stuff with Elixir. But before we do that, I want to give everybody just like a little bit more background about like what the heck Sonic Pi is. They may have not heard
what is
it.
Yeah.
Yeah.
It's a thing for the Raspberry Pi so far. That's what we've got.
Yeah, so something that runs on the Raspberry Pi. Can you explain the project itself?
Yeah, I mean, the mission it goes back to those original days of the Raspberry Pi Foundation, focusing on teaching kids how to code. That was their charitable mission back then. And so Sonic Pi is a piece of software designed to go into schools, to collaborate with teachers, to teach the, as then, still pretty much the same, computer science curriculum here in the UK. And so it was there to teach the fundamental of data structures and algorithms and all that kind of good, logical computer science stuff. But it turned out the real problem wasn't can we teach these things? The real problem really is how do we engage the kids? How do we get them to care? So Sonic Pi isn't just a tool to teach those basic concepts. It's actually a musical instrument that needs those basic concepts to make music. So you kind of learn how to code by making bass lines and drum riffs and drum breaks. And so they're both are very tightly coupled. You can't really tell that they're apart. But it's really using music as a tool for engaging the kids in the computer science.
Well, I should say my first project when I was at university learning computer science for like our first code camp, which was like, I want to say I was a sophomore or junior, was I built this Python script that I hooked it up to a microphone and put the microphone right next to the drum, tap the drum beat, and it would just detect like the actual beats. It wasn't sophisticated enough to have like loudness or any specific notes, but you could play a drum beat into it and it would kind of map out what the drum notation was for that drum line that you were playing.
Sweet. So you'd look for the energy transients and see where there was an energy change and trigger and just log that as an event.
Yeah, exactly. It was just looking for peaks.
Sweet.
And then it was kind of logging them out. It worked, but like not super well. Like definitely not to any like practical. But the point is, I had so much fun building it, and I can see how. I mean, I looked at Sonic Pi. You basically write some Ruby-looking code. Is it actual Ruby or is it just Ruby-like?
So the DSL for the Ruby language is implemented in Ruby, and for the most part it is, but there's a tricky sort of boundary because I've taken the language and sort of warped it in ways to make it more like a musical instrument and less like a tool for building a web server. There are some edge cases where it doesn't behave exactly like Ruby. So although it is Ruby, I tend to say that it's Ruby-like and all the language in the documentation is very well documented. That's what's supported. And then a ton of Ruby stuff will work maybe, but it's not necessarily guaranteed to work in the future. So it's very, very, very close to Ruby, but not quite Ruby.
Yeah, okay, that's what it looked like to me.
You don't need to know Ruby to use Sonic Pi. That's another critical bit of information.
Oh, interesting. Okay. I mean, Ruby already reads pretty well like English. I mean, I'm a bit more of a Python guy myself, but like, both these things you can kind of look at it, and if you're familiar with any programming language,
perspective, when you look at these challenges for writing a solution to a program in a way that's the most readable, by and large, I think that the Ruby solutions tend to be the most clearly communicating the domain that they're trying to implement. Although the solutions are typically very inefficient, often wildly inefficient, I feel like Ruby's a really nice sort of sweet spot language for being really, really clear and expressive. And there are a bunch of things actually over Python which I think are critical for the educational domain. And I mean, I'm happy to talk about the differences of programming languages. I'm not flying one particular flag in favor of language A, but I think certainly when you're learning, like let's think about drawing. If you're learning to draw a circle, I think it's important to be able to draw a rubbish circle as your first circle, right? And like when you start to walk, it's important to be able to sort of stand up and fall over. And so I think that drawing a circle, if you try to draw a circle and it wasn't perfect and then your teacher told you off, that wouldn't be a very nice learning environment. And I think that programming languages which support messy programs, that support flexible syntax, although that might not be seen as very professional, is actually probably quite a useful aspect or sort of functionality or feature of a programming language for education. So I feel actually Ruby has that advantage over Python. So in Python you have to put the parentheses for a function call, in Ruby you don't. And Python has like hidden invisible indentation, which actually is semantically meaningful, which is super useful when you're a professional Python programmer and you're moving from project to project and all the indentation is the same and it all feels very familiar. But when you're learning these things, actually, why is this invisible thing that I can't see affecting how my program works, can be quite a big obstacle. So I feel that Ruby has a bunch of interesting little small, and they're only minor, differences from Python syntactically, which actually I feel make it much more friendly and forgiving in a learning environment.
I've never really done a lot of, I shouldn't say never. I've done Ruby in the past. I've done a few other programming languages that don't use the parentheses. The parentheses so we teach a lot of students on Boot Dev. Haven't had many issues with parentheses in terms of like teaching students how to do a function call, but the indentation thing is a big is a big hang up. And the fact that in Ruby it's not a problem. I mean, I don't think it's a problem in any language really, to the extent that it is in Python, where it's like, you have 3 spaces for indentation on one line, and as a beginner you're just sitting there pulling your hair out.
Entirely. Or if you're a teacher, and this is the thing in the UK, and it's actually quite true across the world, is a lot of computer science teachers don't have a degree in computer science. So when the students put the hand up and you go over to help them, and there's a problem exactly like describing, there's an indentation issue that no one can see, that's really difficult for the teacher to help the student as well. So tools which don't just make it easy, but clearly, as best as they can, communicate the problem so that the student and the teacher can actually figure it out are really advantageous.
Yeah.
Yeah.
Okay, really quick. I want to give everyone that's listening like a really solid example of Sonic Pi. Loop, do, sample, perk bell, rate, random, 0.125 to 1.5, and then sleep for a random amount of time. And I'm going to go ahead and play it. So it's just like, it's randomly giving me different pitch of bells, but it's really cool what you can do with, this is 4 lines of code. I'm guessing you've built some pretty complex stuff with this.
Yeah, so what you're seeing there is, so Sonic Pi is a tool for making music, for teaching computer science. And obviously, as a goal, it has to be super simple. So it has to be something that the teacher, we're talking about sort of indentation issues, but just the syntax and just getting to be familiar with it has to be really simple. And so a large part of the design of the language turned into, what can I slip into the language? How can I fit it in a way that it adds creative possibilities and interesting musical ideas, but also doesn't interfere or make hard teach the basic computer science. Yeah. So you're kind of seeing there like a combination of all those things in a very simple way, but actually can be quite expressive and creative. What Sonic Pi is doing in this case is it's triggering a really powerful synthesizer called SuperCollider, which is an open source synthesizer which runs like Nginx or Apache, so sits there in the background, binds to your audio cards, and has a network API. Oh, okay. And you can talk to it straight over UDP or TCP and send it messages and tell it what to do. And so in this case, Sonic Pi is telling it to load up the perk bell sample, which is a pre-recorded recording of a bell. So that's just an audio file of the sound oscillations, how the sound moved. So the microphone moves as the sound waves hit it, and those movements are recorded as numbers, and then they're played back to the speaker. But when you play it back, you can play it back at different speeds. So you can play it back faster or slower than the original sound, and that actually happens to change the pitch. So when you play something twice as fast, it actually is an octave up. And then in between that is all the different possible notes you might have. So, and then of course you can play it backwards at different pitches as well. So you're hearing there is that percussive bell being played at different playback speeds and backwards, and that's the change of the pitch and the change of the timbre. And then that sleep as well, that's the critical thing, is that the sleep 0.5, I think it was, whatever the sleep time is, it's extremely accurate in Sonic Pi. So that's another critical thing, because we haven't talked about this at all yet, and hopefully we will in a moment. But it's important to when you're teaching computer science and you're trying to engage kids, is that it's not just good enough to have something that can teach the concepts. It's not just good enough something that engages the kids. It also, you need something that projects the possibilities, the potentials, that gives the learner the motivation, like, why am I even bothering with this? And so it turned out that with Sonic Pi, if I wanted to really fulfill that it needed not just to be a tool for making simple little sounds that could teach computer science, but actually needed to be amazingly badass professional musical instruments that professional DJs might use on big stages, and it is today. So that's amazing. So all of those ideas then went into making this thing be really, really powerful, but having maintained that simplicity. So you're seeing all those concepts rolled into one, but you're missing out one there. So those examples I wrote almost 10 years ago now, perhaps more, missed out. This is interesting, because the loop you've got there is not recommended to use at all in Sonic Pi. Loops are really crap.
You got to update the homepage.
No, but it's an opportunity to learn. So loops are crap because they are single-threaded. Uh-huh. And once you get a loop going, doing a cool thing, you can't change it, ever, right? Unless you redefine it within itself, then you need to have some kind of hot swapping code functionality. And also multiple loops, if they're concurrent, they might go out of phase and out of time. And so Sonic Pi actually has a really cool concept called live loop, which for all intents and purposes is a loop, but it's concurrent, so multiple live loops can run simultaneously. And also, they don't just run at the same time, which is normal concurrency. They run in time, which is like a band.
So they like wait
Otherwise, they would just
for
be
have some
chaotically.
like synchronizing mechanism at the start of each
They
loop.
have an initial, so they all start at the same time, and then their timing is always maintained so the drift never happens. So they always they're always accounting for the potential drift if the scheduler is doing something or the operating system doing something. You can't always sleep for at least amount of time. You've got to look at where you want to be and sleep for what makes it the right amount of time. So you're always accounting for drift.
Okay, let's talk about that in just 1 second. I want to give one more example. I'm going to have Stas cut in another example here. Sounds really cool, has a lot of stuff going on. To your point, this is kind of like, I want to show people like this is what you could do. Granted, I'm sure you could do even cooler things as well, but like this is a much more complex example of something you could accomplish with Sonic Pi.
And I mean, these examples as well also ran on the original Raspberry Pi 1, so in real time. The sound you're hearing there is a TB303 synthesizer, style synthesizer. So there's actually articles inside the software itself. I wrote a year and a half, maybe 2 years worth of magazine articles for a national magazine in the UK, where I wrote a series of articles on Sonic Pi, and they're all inside the software. And one of them is on that TB303 sound, how it was created, what the oscillators were, in a way that sort of 10-year-old children can understand and read. And you're hearing some randomization there, and you're changing the different... so like these synthesizers I have behind me, for example, there's lots of different knobs. And in Sonic Pi, there's lots of these synthesizers, also with lots of knobs, but instead of knobs, they've got names. And those names are the parameters you can change and manipulate. And you can set them to be any value, but you can also set them to be random values, or you can... any mathematical function you can pass into these things, so you can manipulate them in really powerful ways. And so you're hearing those synthesizers being manipulated and modified by sending different values, which note to play, which cutoff value to have, which filter resonance to have, all very precise. And so, you have the complete freedom to change all the aspects of the synthesizer within Sonic Pi. And also, each of these synthesizers here is quite expensive, but they're free in Sonic Pi, and you can have as many of them as you want until your CPU doesn't really deal with it anymore, which is actually today is an amazing amount of synthesizers simultaneously.
Yeah. I love the idea that I could check a song that I'm working on like into Git, into source control, collaborate on like a line by line basis, make atomic updates, rollback changes. I played with GarageBand as a kid on Mac, but it's a GUI editor. I don't actually remember all the details, but like it's a GUI editor, and it kind of feels like working in like a Microsoft Word document in the sense that you don't have this really robust history of everything. Collaboration's not super easy.
Totally.
I love the idea. I've had this long-standing idea that legal documents, it would be so nice if bills like that were passed in Congress were presented as Git diffs. So you know how like currently the way it works is like you write this 600-page bill and it gets passed, and then if you want to change anything, you write another 600-page bill that just back references to the first one. I don't know if that's sustainable. Like 100 years from now, you'll have to go through so many pages of documents just to figure out what the current law is, where, it would be so interesting if you could actually like redact lines using kind of a diff system. But we're doing...
Totally. I mean, I think that we're spoiled in the programming world with diff. The fact we have text is just so amazing. And I have friends who work as architects, and they don't have the same kind of thing. They can't diff their architectural things as easily as they were. What happens? Like, what's the difference between last week and this week? They've got some sort of tools, but they're nowhere near as powerful as ones we have. And so what you're saying is absolutely really important. I think there's a reason why we still study Mozart and Beethoven today over Aphex Twin, is we have the notation for those composers that's preserved. They're able to read the notation, study the notation, and we can reproduce and reinterpret the notation. And these are all amazing historical activities to do, and we can't easily do that with today's modern music because there isn't really a notation. And so I remember seeing a performance from I think it was the London Sinfonietta Orchestra, where they took some of Richard D. James' Aphex Twin's works and recreated them, and even like broke a piano in the same way that the synthesizer sounded. It must have been really painstaking to reverse engineer, essentially, the composition from the audio to a score to then be played back. And with code, you have access to that score. But it actually spawns a few really interesting things, and one of them, the most important ones, is an argument I have actually with quite a lot of artists, is on the nature of randomization. Because if you have a system which supports randomization, then actually that conflicts with some of the goals you've described about being able to take that notation and store it and then reproduce. Because if the reproduction is random every time, then, I mean, if that's in the design of it, that's understandable. But actually, I feel that that's less useful than something that actually allows you to use randomization to explore, but when you find something you like, to then keep it, to hold on to it, to have a name for it. Otherwise, it's trying to pick up water. It's sort of impossible to grab and hold. And so the whole of Sonic Pi's design, so these are kind of things where they might diverge from traditional vanilla Ruby, is that the randomization system is completely rebuilt to be deterministic and to work in synchronization with the concurrency model, so that there are no race conditions when those sort of deterministic values are calculated and figured out. And so this has a really interesting set of opportunities for taking your code, which includes randomization, and storing it and reproducing it perfectly later down the line in a way that isn't really easy unless you actually thought about this and put it into the design ahead of time.
Yeah. So is that just like an incrementing seed value kind of at the start of the program? How does that work?
Yeah, so the traditional randomization systems, they seem to obviously focus on having high entropy and being good for crypto stuff, which obviously is not the goal of Sonic Pi. So we can afford to have a system that isn't actually very random, but is random enough. But there are actually other properties as well, is that the determinism has to not just work in a single thread, but has to work across threads. And typically, languages will implement randomization by having a single kind of stream of random values, and threads will then just arbitrarily pull off it, like having a single deck of cards, like shove me a card. And so that actually works well for higher entropy because you've got interleaving race conditions there. But that obviously doesn't work well if you want a deterministic state model for your execution. And so all I do is I read in, because it's an audio system, I can have like a 10-second audio file of white noise, which is like a random sort of set of values. And then each thread has a thread local value, which is an index into that list, which then wraps around, mods its size. And so you can just keep calling subsequent next values until you get to the end, and then you wrap around, and that's 44,100 times 10 values. That's plenty for you to be able to work with. And then there are other interesting consequences, like once you've got a system like this, it's actually really interesting to think about a function call which is not just rand, but undo rand. Like, I want to actually put my card back on the pile.
Like, I want to play the randomness and then play it in reverse.
Yeah, undo it, exactly, so that I can do it again, the same thing again. So actually, so you can start to play with randomization as a tool. It starts to become interesting, really interesting. And I have some. There's a university, a music university, a conservatoire in Antwerp, in Belgium, and they're using Sonic Pi to teach the sort of top tier jazz performers. Some actually graduated not just playing on a saxophone, but playing on Sonic Pi. And this is the kind of conversation that they're really interested in, is the randomization and the deterministic values, and playing with that and using it as a tool is, musically, some really interesting possibilities. Yeah,
that's incredible. One question I meant to ask earlier and I forgot was just, how did you get involved in all this? So you were at Cambridge. Like, how did you get involved with Raspberry Pi and then Sonic Pi?
I mean, there's lots of luck involved and good timing. The music thing for me was, I was at a programming language conference in Denmark, maybe 15, 16 years ago now, and seeing the party had some Java developers who just joined together to make a band. And it's like, who can play bass, who can play guitar, let's form a band. It was cool. But I was like, surely it'd be really cool if you could program the music. And so it's one of those sort of throwaway ideas, which then turns into the next 17 years of your life. And and so I started studying it and figuring out and learning. Obviously, once you've had an idea, you realise that people have had that idea since the time began, and even go back as far as Ada Lovelace, and when she was working with Charles Babbage on the sort of analytic engines and the difference engines, she was imagining these big mechanical systems could be becoming musical instruments, could make algorithmic music of any degree of complexity or intent. And so that was, these ideas are not new, and since people have managed to figure out how to make a computer, they've managed to make them into musical instruments. But it's only recently, sort of the last sort of 15 years, 10 years, that we have computers powerful enough in our homes to not just make music, but to make music live. So in the same way you might watch a Toy Story and you know that each of the frames in Toy Story took a render farm 2 weeks to render with all the lighting.
Yeah.
And so you spend a whole bunch of time rendering the film and seeing it live. That's not real time. Whereas you're playing Quake 3 in the old days, that was real time. And so music live in terms of synthesis, make it live, only fairly recently became a thing that computers can do. And I think that's what I've been particularly exploring, is how we can manipulate and work with that in a way that's natural and expressive, but also could be used to teach computer science.
Yeah. So the feedback loop, I mean, you edit the Sonic Pi code and like you can instantly play it.
Yeah, so the Sonic Pi code runs in the Ruby interpreter at sort of human speed. You sort of got loops which are spinning around 8 times a second, or 16 times a second. No faster than that, really. And what they do is they run slightly ahead of time, and they have each thread has its own local clock, and it's using that clock to figure out when it wants the events to happen, and then sends those events with a very fine granular timestamp to the synthesis engine to say, at this time, can you play the synthesizer? So although the Ruby language is slopping about and garbage collectors happening and like it's not super fast, as long as it's sufficiently ahead of time and it's got the good timestamps and it sends them in a sufficient amount of time ahead of when they need to be played, then the supercollider synthesis actually takes charge of taking that timestamp and parking it to be exactly that time, and has a really efficient, well-timed scheduler, which is implemented in C++, which has like no mallocs, for example. So they've really spent a lot of time to make this thing really well-tuned, performance, time beast. Supercollider is amazing for that. So yeah, so the Ruby part really just takes care of figuring out which synthesizer to play and when, and particularly the timestamps, and then hands all that stuff to Supercollider.
Yeah. Kind of parsing the I guess the musician's input.
Yeah, so it's a programming language input that generates a whole series, of tons basically, of network events using this protocol called Open Sound Control. But they're little binary packets that say, at this time, play the synthesizer with these values, essentially.
So if I edit the code, do I have to restart? Do I have to restart from scratch, or does it is it like on the next loop it'll pick it up? How does that live coding aspect work?
Yeah, I mean, so these are all design decisions you would make building a language like Sonic Pi, and actually there's a ton of different live coding languages out there. And so if the idea of a live coding language is new to you, if you're listening to this and you think, oh, okay, actually go and check out, there's a whole bunch of different ones, and they'll all make different design decisions about how to turn the code into an execution of sound. In Sonic Pi's case, the goal was to try and make it as simple as possible in terms of teaching computer science. And so there, I couldn't really go too esoteric in terms of language design, even if they had some interesting sort of didactic values or benefits. It had to be something that the teachers could feel a bit familiar with, so it had to be something simple. So I stuck with traditional concepts and then tried to put the music into that. So yeah, so I've gone off completely off a tangent. I've forgotten the question again now. So sorry, can you remind me the question?
No, yeah, just wondering, like, so if I edit the code as I'm composing, when does it? When does the next
So
loop
in Sonic
happen?
Pi's case, you work as a sequence of instructions, so it starts at the top of the screen and works its way down. If this instruction does not talk about time, which most of them don't, then it's assumed that instruction takes 0 time, so they'll all work concurrently, which means that the events that instructions end up generating will all share the same timestamp if there's no mention of time. And then when you do talk about time, that advances the logical clock for that particular thread. So the next event then will be played at the time plus whatever it is that you slept for, that you modified time. And so you're essentially managing a bunch of threads. So Sonic Pi is like a poor person's Erlang OTP. I've got a whole sort of thread model I had to implement that lets me drive a bunch of threads. Each of them has its own notion of time. Each of them are sending events to the Supercollider synthesis server. And then I'm coordinating and managing all those. And so they're in terms of updates, well, so far I've got a system now in terms of what I've described is each thread can start at the top of the program and work its way down. So it's like a sequence of instructions. But of course, you can imagine putting that into a loop, and that will just spin round. But as I said right at the beginning, if it was a traditional loop, that thread would just sort of stay there in that sort of pattern forever until you kill it, which is not particularly useful when you're performing. And so the Sonic Pi live loop was an idea essentially converting something I'd seen before. So there's a really nice system called Impromptu. And this system was an old Lisp system for making music. And that had an idea of temporal recursion. So you'd have a function which would then schedule itself to be called after a particular amount of time. So this is by a guy called Andrew Sorensen. And this idea was really interesting, but obviously recursion and temporal recursion and scheduling are all quite sophisticated concepts that aren't easily injected in a computer science lesson that's right at the start. So I just sort of inverted that. I made this idea of a live loop, which is a loop which is backed by a thread, so it spins around on its own, so you can have multiple live loops running at the same time. Each of those threads has its own notion of time, but at the point where the live loop spins round, the live loop, actually its implementation is to call a function definition, which is the same name as the live loop. Each live loop is a thread, a loop, and a function. And you could update the function's behavior, so the next time the loop spins around, it calls the new function. So there's a sort of atomic semantic on terms of the function. You never swap it halfway through the function execution. So if that function was to take 10 years, well, that live loop will take that 10 years before it spins around, even if you update it. So as a musician, you're constantly thinking about which are my fast live loops, which are my slow ones, because if you update the fast ones, that you'll hear the result much quicker. But maybe you've got one which is spinning around every sort of 4 beats or 8 beats, so you're talking about the next groove or the next section of the music with those longer live loops.
I see. So it always takes at least one. You've always got like one more loop before you before you hear your change.
At most one, but it could be just if you just do it, if you time it right, you can just be there before the next one flips in.
I see. Okay.
Yeah.
At most.
But that approach allows you to then be more clear about what the timing of that is. If it was to be when you press the run button, like if anything's related to when you physically press go, then you're in a real tricky situation of making sure you press that button exactly the right time, and that's not always possible.
That's why you could use it for
latencies.
Live music, right? Like you actually be up there.
You can do that. Yeah, but by default, it's easier if everything's just lockstep in time with a clock. Yeah.
I feel like you would only do that if you like to live dangerously, like. Because you could code it all out ahead of time, of course.
Yes. No. So in Sonic Pi, you typically work in two different ways. One of two different ways. One is composition mode and one's performance mode. So in composition mode, you're treating it more like a traditional programming language where you're just writing a script that starts and finishes. And in that script, you can call in thread, which allows you to spawn threads, but that's typically just to make it easier to write the bass line to run at the same time as the melody, for example. Rather than trying somehow to weave those lines together, it's easy to specify them individually and just tell the computer to play them at the same time. So composition mode is really about writing the code and then pressing play and standing back and hearing the results. Whereas performance mode is really just using live loops. So you just have a bunch of live loops, you start them off, they do very simple things. The combination of them makes a sophisticated thing, and then you keep modifying the live loops during the performance, and that changes the music and takes it into interesting directions. Which then begs the question about, like, how do you deal with errors? So it's often you'll have a live loop and you'll type the code and it's a mistake. What happens then, and how do you fix that? And these are interesting conversations that come in when you not just build a tool that's teaching computer science, but now you're working on something which is supporting the artists to perform on the stage. Because you could just press stop and start every single time you want to do something different, but in a performance, you can't really do that.
That makes sense. So let me guess at how it works, or maybe how you want it to work. Like in a normal programming environment, like if you have a syntax error, for example, like everything just breaks, and it's like, come on, fix the bug, and then we'll keep going. My guess is with Sonic Pi in like live performance mode, it's probably better to just keep playing whatever was there before and allow the programmer to finish typing or to like fix the typo and resave and then commit the change. Is that kind of how it works?
Yeah, I mean, so you're getting there. So the idea of committing is really critical, I think, and that's the idea that the performer says, I'm in a place now where I'd like the computer to see what I've written. There are live coding systems which are always auto-reading what you're saying, and as soon as you make something that's valid, it starts doing stuff, but it's really easy to be in a state where you're not where you want to be, but somehow it's valid, and then it's doing something that you didn't necessarily intend. And you're flipping between valid and invalid. So Sonic Pi doesn't do that. You have to press the special shortcut to say, commit the code. So at that point, you've got a clear point where you as a performer are happy with the code. It still might have errors, right? So the two kind of errors it's going to have is a syntax error or a runtime error. So with the syntax error, it just goes, can't read the code, and nothing has changed. So if you've still got running processes in the background, they still are running. So if you've got a basic beat in the background, that basic beat's unchanged. So essentially, you've tried to modify the running process, but the computer just won't let you. So you fix the syntax mistake, and then you press run again. Then it commits the code because it can read it, it can interpret it, and then that code, if it's in the case of live loops, will update the functions which are the defining behavior of each live loop. So when they spin round, the new behavior kicks in. But when the new behavior kicks in, and that itself contains an error, because you might just have typed the function name incorrectly, so it's correct syntax but semantically incorrect. That point, that thread that reaches that error will die. And so if you've only got one thread in your musical performance, then everything stops. Hopefully you've not done that. Hopefully you've got one thread doing the kick drum, one thread doing the bass line, one thread doing the melody.
Your drummer lost his stick, right? Like dropped his stick.
And so that thread, just the one that you made a mistake, dies. Usually the audience thinks that's cool because you think you've intended that. And then your job then is to fix that mistake. So this is the thing where I didn't actually have an easy solution for this, because programming languages, as you said, when you get that situation, you tear everything down, you clear the database, you reverse all the migrations, you reset, and then you run all the tests again, or you try it again and see if it works. You don't have that opportunity when you're performing live. So you need to be able to fix the mistake find what the mistake is, fix it, but then you need to be able to start the new thread, because the old one died because of the mistake, in a way that's in time with everything else. So in Sonic Pi, there's actually explicit semantic functions that lets you start threads in time with events that are created, so that they are lockstep logically in time with each other. So you can essentially use any live loop as one of these points, or you can even create them manually. You can also map them onto external events like network messages or MIDI messages. So any event coming into the system or generated can be used as a point to say synchronize. And so you can use another live loop and say, when that one spins around, start the one that broke, and they'll be back in time with each other. So there's the syntactical words you can write to make sure that's the case. So you don't, as a performer, have to press the start button at the same time as the beat and try and sort of get it right. Because if this didn't happen, you could start that thread. It would be in the same tempo, would be out of phase with the original music. So it's about getting it back into phase.
Oh, that's cool.
Does that make sense?
A lot of interesting, and a lot of
concurrency. So not just in time, not just at the same time, but in time. That's the sort of difference. And when people talk about concurrency, they already go crazy and go, it's too complicated. But this is concurrency with the added constraint that these threads need to be a time aware of each other as well as just running at the same time.
Right. Which, I mean, as the programmer of a song, would make your life easier, I imagine, not having to worry about drift and all that kind of thing. Have to
100%, exactly, yeah. And when you're performing and it's like you're in a big nightclub and it's 2 a.m. and you might have had a couple of drinks, you definitely want a system which is simple to work with, that's tolerant of your mistakes. And when you do make mistakes, and you can't avoid making them, like we can talk about type systems or formal validation or proofs or whatever, you're going to make typing mistakes. They're just going to happen of whatever kind.
Yeah.
You need a system that's tolerant to that allows for it and allows you to fix mistakes in a way that doesn't require you to stop everything.
Right. Okay, I want to talk now, shift a little bit. I think you did a really great job of kind of explaining from the user, when I say the user side, I mean like the musician side, essentially, what Sonic Pi is and how you use it. Let's talk about the implementation a little bit, because you mentioned early on Erlang and Elixir, and then there's also kind of, you said the Ruby language is also parsed by Ruby. Can you talk about how those different components kind of fit into the architecture of the project?
Yeah, I mean, right from the beginning, the goal was to build something that ran on the Raspberry Pi. I was working on a system called Overtone at the time, which is a Clojure live coding environment, which runs on this Lisp called Clojure on the JVM. Super cool system. having a lot of fun with that. And so I took a lot of the design from that. So I needed to do two things. And then that was also the same. That sat in front of Super Collider. So Overtone was a closure front end to Super Collider. So the idea of using Super Collider as a synthesis engine made sense. It was written many, many years ago, sort of 20, 30 years ago, I think now, on Mac OS 9. So Super Collider had no issue running on the original Raspberry Pi. Ruby had no issue running on the Raspberry Pi. Clojure did at the time. The JVM was not well supported, though back then. It didn't. I think the JVM didn't even have floating point support.
Okay.
So, yeah, trying to get Overtone running on the Raspberry Pi was a non-starter. I only had 2 weeks, really, to build the first version of Sonic Pi, it turned out, because it was a 3-month project, and in those 3 months, they wanted me to build a system, to find a teacher, to work with the teacher, design a curriculum, teach the curriculum, and assess it in 3 months. So I recognised that it's easy to spend 3 months just doing a prototype for a language, never mind all those other things. So what's the smallest thing I could build in 3 weeks, 2 weeks? And so I took the Overtone design, made the simplest thing, which just made a beep with Super Collider, and then wrote a GUI in front of it, which allowed me to then obviously have an editor and to display the errors and to display what it was doing. And that had to also be, the choice of that was constrained by the original Raspberry Pi, so it needed to be super efficient. So I used Qt, and C++, and used its widgets to build a text editor that had syntax highlighting, etc. So from already, we've got Super Collider, the audio system. We've got Ruby, the programming language, which allowed me to build a very simple front end, which just said, like, play a note, sleep for some seconds, play another note, sleep for some seconds, and you can make a melody. And that was what Sonic Pi was for quite a while. It was just the C++ GUI, the Ruby runtime, and then the Super Collider synthesis engine. But at some point, I wanted to add other functionality. I wanted to add MIDI. I wanted to be able to plug in a MIDI keyboard and play that and see them as events. I wanted to be able to trigger MIDI keyboards in the same way I could trigger Super Collider. So I already have a very simple expressive thing to say, play a note. It'd be nice to be able to say MIDI a note and have that just send the MIDI message to my connected synthesizer like I've got behind me over USB. And there's also a bunch of other things I can go into detail as well, terms like network interfaces and communication. For all of those, the outgoing messages needed to be well timed. So it's not just a case of I'd like to send a message straight away. It's I'd like to send the message on the beat. At the same time I'm hearing a sound, I'd like to flash my lights. And so I wanted to write a good scheduler for that, and I wanted it to be accurate in the same way Super Collider's was, and it uses all sort of super fancy low-level C++ stuff, and as I mentioned before, it allocates all the memory ahead of time. You've got like a whole heap that's been allocated, and it works within that, and so there's no mallocs during the execution, and all this good stuff, and this is all way out of my league. And so I looked at trying to be able to sort of take that and modify it and just make it something that could do MIDI, and in the end, I wanted to build something that allowed me essentially to have a thread per timer, that thread was able to sleep for the amount of time it needed to in isolation. They didn't interfere with each other, and it just worked. And turns out that this is kind of exactly what Erlang can do. And I was having a conversation with Joe Armstrong, who was one of the co-creators of Erlang, and he was just super interested in this. And 2 weeks later, he came back with a prototype, and he was excited to work with it. So I worked with Joe for a while on that. And so he introduced the idea of having a well-timed scheduler implemented in Erlang that let me start to send MIDI messages and network messages in time with the sounds. And of course, then it made sense to use the same system for receiving the messages. Erlang is amazing for doing network stuff, low latency. So we had a whole Erlang subsystem. And then I started exploring with Elixir. I think Elixir is a really beautiful language, has a much more vibrant community. And I wanted to also explore web stuff as well. So it made sense to shift from Erlang to Elixir. And if people aren't aware, they're both very similar languages with quite different syntax, but essentially the same sort of thought model. And they run on the same virtual machine called the Beam, which is like the JVM, but it's designed specifically for really high concurrency, high availability. Like weirdly, like 30 or so, 40 years ago when they built it, it was for esoteric ideas that no one else needed, but turns out to be pretty much all of today's modern applications need to be on the web, need to be highly available, need to have hot swapping code. Yeah, like the throughput of the messages. It's not about like the JVM focused on getting high throughput, and actually then turned out that if you have that one message which took too long, that's a whole ton of business gone. So actually having systems which are low latency as well as high throughput are different trade-offs. And Erlang was focusing on that. So, and it turns out that when you're building a music system, at least the way I'm building it, it's a highly concurrent message-orientated system, sending tons of time-stamped messages within itself and working with those. So, yeah, Erlang turns out to be a really good, or Elixir, sort of architecture for exploring this.
Okay, that's so cool. Let me say to you what I have understood of the architecture, specifically like the flow of information from like when the musician types it in to like when it comes out of the speakers, and then you can correct me when I'm wrong. Okay, so I'm working in this GUI that's written in C++.
You double click and you get an application. That's the first thing.
Yeah.
A lot of live coding systems don't even have that. It's just you download the app and you can start it. That because this goes back to just to interrupt. So they when I was a kid, I had a ZX Spectrum, and it came with a manual. And you open it up, and you could write your first programs, and it was literally print high, and you could print on the screen. You can make a beep, and the way to make the computer do something was so low friction. It was incredible, and that got me hooked. And today there is nothing like that. So Sonic Pi, just to interlude there, is not just about all the things you described. It's about making that in such a way that anyone can just download it and get started. So yeah, you can super easy get to that first point where you type in those first words in.
Yeah. Okay. Also, just to interrupt myself as well, low friction is super important. We start students on Python at BootDev, and we move people out of our in-browser editor later and have them code on their own machine. But we think it's super important that you can just go to boot.dev in your browser and start typing Python code and run it. Like in
the same interface as everyone else, and so you can help them out. It's all much easier. Yeah. Totally. So yeah, Sonic Pi was like, and it's like going into a school, you've got a computer science teacher that's not done the computer science degree. It's the same problem. Like, how do I get this thing running on the school computer?
Yeah, like God forbid the teacher has to like install virtual environments and stuff. You don't want that.
No, so that's why I've got a Windows version, for example. I've done a ton of work on Windows to get that just to work straight away. So yeah, so you open up Sonic Pi, you've got a text editor, you're typing your first words.
Very good. So I'm kind of interfacing with the C++ code at this point. I'm typing words. Then
the Ruby code.
Oh, the Ruby.
You're using the C++ editor to type Ruby
C++
in.
editor. I'm typing in Ruby code, but this isn't your Ruby code yet. It's my Ruby code. And then at some point I like commit it, and now some Ruby
press
parser.
The run button.
I press the run button.
Yep.
Some Ruby parser is now going to like parse the code that I've written.
The C++ editor takes the code as text and then sends it to the Ruby processor to then evaluate.
Got it. The Ruby
and then
processor
Ruby then just runs it like a Ruby program.
Runs it like a Ruby program, but then at some point the Ruby program is emitting something to this like Elixir Erlang background process.
Well, so at some point the Ruby program has side effects. Those side effects are to spit out network messages, and those network messages go to two different places. One is the traditional place, which is the supercollider synthesis engine to make the sounds. So when you're hearing those sound perk bells, they're all messages from the Ruby to the supercollider.
Okay.
But if you're doing any I/O, sending messages out across the network or to MIDI, then that's going to Erlang, and then from Erlang out of the machine.
Okay, I just want to understand the difference. So is it that like, is it the Erlang and Elixir processes that's for like events that are scheduled in the future, whereas the other one are instant? Like what differentiates those two?
Oh, both are for the future. It's just a supercollider. Its schedule is only specifically for its audio system. So you can schedule only synthesizer things that supercollider can do.
I see.
Whereas the Erlang thing is for scheduling arbitrary things.
Got it. Basically anything that's not supercollider.
Yeah, anything else. Yeah, exactly. And it's not as well. It's within a sort of 10 milliseconds window of accuracy. It's not like super accurate, but it's accurate enough. And certainly when you're sending things across the network, unless the only way to fix that is to actually have a scheduler on the other end and do the same trick of sending it ahead of time and parking it until it needs to be executed.
I mean, it's more accurate than my hand when I'm hitting a drum.
Yeah,
so
yeah, absolutely. And it also accounts for drift, right? So you might get some jitter, but yeah.
Yeah. Okay,
yeah,
very cool.
type the code gets into the Ruby then sends events to either Erlang or SuperCollider. Erlang for I/O, SuperCollider for audio.
Yeah. Awesome. Okay, cool. I really like that. Thanks for walking us through that. And again, for everyone listening, sonic-pi.net.
Yep.
Go check it out.
Just Google Sonic Pi, yeah.
Yeah. Okay, cool. Now, I want to shift the topic of our conversation just a little bit because, so Sonic Pi, my understanding again, correct me if I'm wrong, open source project and kind of funded by, well, I'm assuming the model may have changed over the years, but it's primarily funded by sponsorships and donations?
Yeah, I mean, so originally it was that sort of 3-month grant from the Broadcom Foundation, who make the chips for Raspberry Pi. And then the Raspberry Pi Foundation also then was super kind and funded it for a couple of years. But then their charity went in sort of different direction. They've changed their charitable mission now. And they're doing similar related things, but I think that the idea of a music synthesis engine for teaching computer science wasn't directly what they wanted. And so they stopped funding. And at that point, I then had to make a decision about whether do I carry on at university, trying to find grants and funding to do this, or do I try and make it on my own? And I really wanted to maintain the freedom that I had, which up to that point was really quite unusual. I was given a complete freedom, essentially, to build what I wanted. And that's why Sonic Pi exists. And so I wanted to see if I could carry that on. So since then, every time I gave a talk at a conference, I charged money. And if they didn't pay, I couldn't talk. And so that was like, if I can't make this happen. And so that paid for a whole bunch. And then also there's lots of donations from Patreon. And I'm making a video series now, which is making some money as well. So if what you like listening to is interesting to you, you can get started with a really super simple video course, which I've made. And so the combination of all those things has given me...
We got to tell them where they can find it.
Oh, yeah. Well, maybe there's like a link at the bottom. Or like, just Google Sonic Pi and go to the website. Okay. It's directly there. Yeah, and so, yeah, a combination of all those things allows me to keep going. But it's really about multiple revenue streams, not a single one. Because like COVID hit and then all the conferences died. And so if that was my only source of income, I would have been stuffed. So having a bunch of different ones is really critical.
Yeah. So have you been full-time personally on Sonic Pi since inception?
Yes, absolutely.
Oh, wow.
So yes, like 10 years
that.
now.
Okay.
Yeah, and I mean, like the last sort of 5 years independently, it's been tricky, to say the least, and I've had to make a lot of sacrifices. But yeah, so like I definitely don't earn as much as I could have done if I was taking a traditional programming route. But I have the freedom to hack on the things I want to hack on and build stuff which is for the public good and for human expression and things I really believe in. And I feel that's a really important thing to do.
No, that's really cool and really impressive. I mean, it's not easy to build Sonic Pi, and I imagine it's maybe even harder to fund Sonic Pi when you're doing it like full time. So that's incredibly impressive. Yeah,
and so that's massive thank you to everyone who's supported me in any way. Actually, and there's quite a few different people. And yeah, those who've supported me on Patreon, for example, have been the backbone. They've brought in about half my income now for the last 3 years. And without that, I really wouldn't have been able to survive, because that's paid for the times where I've got nothing. And so yeah, that's been amazing. And then I've had some corporate sponsorship. I mean, Dashbit, Jose's company, have supported me this year, which is really kind. And yeah, so that. But and in order to keep projects like this going, it's really critical to find ways to support it. And the biggest thing I've had to do at the moment is just essentially hold my hand out a lot, like begging all the time. And it doesn't feel the best, but at the same time, it's enabled me to maintain my freedom. So there's always you've got to do a bit of both, So yeah, it's a tricky one. If I got a really good sponsorship by a company, maybe they would lead me and tell me what to do, and that wouldn't be the same.
Right. Yeah. I mean, a lot of times a sponsorship will come with sort of strings attached. I guess what I'm curious in is like, is this like, do you like this model? Do you want to try something different? Are there certain issues with the model that you're addressing such that maybe it's easier to support yourself going forward? I'm curious, like, I imagine you think about this fairly often. Yeah.
I mean, at the moment it's super tricky because finances aren't great. I've just gone through a big house move and house renovation, which has sucked up all of my funds and my emergency funds.
What do you mean? Real estate's super cheap right now. Everyone knows it.
Yeah, I mean, when we moved, we had no idea how much the prices of everything would go up dramatically, like 2 or 3 times. Yeah. But yeah, that's really the critical issue is sustainability. I'm happy with the model, but I'm not happy with the sustainability. I don't bring in enough each month to feel comfortable. And so it's finding a way to just, and I don't need much. I don't need tons of money. I just need enough to pay the mortgage and the bills and feed my children. And so in the big scheme of things, it's not that much, but actually it's tricky getting it through. So this is one of the reasons why I focus on the video course. If I can increase the amount of regular sustainable income, then the money from giving a talk or a performance or a workshop will then top everything up, and that would be nice. But yes, that finding a way to increase that sustainability is the really, really tricky thing. And so people ask me how I'm doing it and whether they were, and how they could emulate it. And it's just, there's a ton of sacrifices you have to make. And yeah, it's not been fun to do that, but at the same time, it's enabled me to carry on. So there's a real balance there.
I mean, BootDev's not a nonprofit, and so I don't have a ton of visibility into like donation. Well, I mean, not that you. Donation and nonprofit are not necessarily the same things. Those are all
so Sonic Pi is non-profit either. It's not a non-profit because in order to make a charity, like in the UK, to make it non-profit, there's a whole legal complication involved in that, and you have to have a board and have to go through a legal process in order to get the status of being a charity, and that just is way unwieldy from my size of Sonic Pi, which is essentially just me. So I do have a limited liability company, and so that's just a shell that the donations can go to, which I then use to pay my salary, or pay myself to live. But all donations go into that. Yeah,
okay, that makes perfect sense. I mean, because the idea of like, and I know it's also probably different in the UK and the US, but like non-profit and for-profit are oftentimes decoupled, and then the idea of donations versus like paid stuff. A lot of times. Yep. You can put out a lot of stuff for free and then have some paid stuff. So I guess that's my next question is like, obviously Sonic Pi is free and open source. Super cool. These video courses. So are you selling the video courses? Is that like how you're plan to make more sustainable revenue?
That's exactly the plan. Yeah. So, I mean, the goal is to make sure the software is always free. I got messages today from people who work in the Education Institute in India, in Italy, for the government, and they're teaching Sonic Pi in schools there, and they have a strict policy of only teaching open source software, and Sonic Pi wouldn't be taught there if it wasn't free, and that's really critical to me to lower the barrier to entry. And one of the barriers is complexity, and one of the barriers is installation, but one of the other barriers is cost. And so getting that down is really important. So I really want to do that, but at the same time, obviously, I need to pay the bills. So the donations is one side, but the course is another thing. If people actually like what I'm doing and they want to learn more, then maybe they're prepared to pay a small fee to learn directly from me, teaching them to do interesting things with Sonic Pi without them having to like try and figure it out themselves. They can get quickly started doing interesting things. And so I've got a very nice introductory video course from complete scratch, assuming you know nothing about programming or music, although if you know a bit about either, that's going to help. But a lot of programmers don't know music, and a lot of musicians don't know programming, so it's really important to cover both of those bases. And even then, a lot of programmers have never used concurrency, or a lot of programmers have never used live programming techniques. So even if you might be a seasoned programmer, there's a ton of stuff actually that you probably haven't spent a ton of time doing, or not necessarily so familiar with, that you'd definitely value from starting from an earlier, easier position.
Yeah. No, that's really cool. I think that's a great model. I mean, I think, like, obviously video courses are a fairly well-proven model. The fact that you're able to monetize through optional video courses and keep the core thing open, I think is great. There's been a lot of
still early days.
We'll see. Hopefully the courses sell. I think, as I'm sure you're probably aware, there have been a lot of different open source models over the last, I mean, at least in my memory, 15 years. And I've heard a lot of discussion surrounding them. And that sustainability point is really critical. And I would argue it's non-trivial, right? A lot of times a project will get started, someone's really excited about it, they get it going, it gets some legs, and then you realize, oh no, if I want to solve all of the problems that my users are asking me to solve, if I want to ship all the features my users are asking me to ship. I'm going to have to work full time on this, or maybe I even might need some of the contributors to work more on this, at which point you need like a sustainability plan. And we've seen tons of different models. There's like the open core, which I think is what, I'm going to butcher it. Did Elasticsearch go to open core? I'm not even going to speculate because I can't remember, but open core is like where the majority of the software is free, and then like there's paid add-ons to it, and that's kind of how you can sustain. This is obviously different, where the entire software suite is open source, but there's paid content on the side. I think Vue does a similar thing, the Vue JavaScript framework, where they have, again, I think, you'll have to fact check me on this, listener, but where they have, the software is all free, and there's like some paid courses linked on the site that they kind of use to fund themselves. And there's definitely been lots of success and failure stories with different models. BootDev's model, just for everyone listening and for yourself if you're curious, it's actually kind of interesting. It's almost the opposite, in that all of our like learning content is free, and then there's all these interactive tools on BootDev, like running the code in the browser rather than it being like a read-only blog post, or using our CLI tool when you're on your machine to like verify that you did everything correctly. It's like paid interactivity, but free content.
Makes sense. Yeah.
And yeah, picking a good model.
And you also open up a whole can of worms when you start talking about growth in terms of the team and managing or working with a bunch of other collaborators, and that's also a whole different kind of worms in an open source project. And Sonic Pi, we've had some really good, fabulous sort of core team members doing some amazing work, but it's generally, I found it almost an impossible task to try and keep everybody on the same page, going in the same direction, whilst also not being able to pay them. Because people are typically only ever interested in doing interesting work for free, of course, and actually a lot of the important work is just drudgery, like, Sonic Pi is not working with the Japanese keyboard layout. The shortcuts aren't working.
Yeah.
Can we fix that? And so, I end up doing most of the drudgery, but then have to be really careful to make sure that any interesting work people do, I can understand it, because at any point a contributor might just disappear. And often they do. Here's a cool thing I've worked on. Here you go. And you're like, oh great, I'll bring that in, and then poof, they disappeared, and then suddenly you've got a whole bunch of technical debt that you've got to maintain that maybe you didn't fully understand. So I found that also really a very tricky part of the project is sort of managing the expectations of contributors in a way that is also sustainable, and that's an interesting problem, without being able to pay them. If I had big pockets and I could just pull in cash and say, you did an amazing job, here's the cash, and here's a really mundane piece of work, here's some cash, that will be much easier to do, but of course you don't have that.
Yeah. Yeah, I think a lot of people assume when they're pretty new to software and open source that any contribution is helpful if it's free. Like it could only be a positive impact on the project, assuming it was like done for free.
Which is so untrue.
So unbelievably untrue. Yeah, we've had so many requests for like, if you would just open source this part of like, your website, we could just fix it. And the problem is, of course, it's like, yeah, but then we have to have all these discussions about how you're not following our coding styles, and we're going to have to review, maybe 5 out of 6 pull requests we're just going to have to close, but we had to spend time reviewing them.
Yeah.
Totally. It's a more complicated question than just like, it's free, so it's good.
Yeah, absolutely. I mean, I'm working on the sort of successor to Sonic Pi now called Tau 5, which is purely Elixir, and I'm just doing that on my own at the moment because it's just fun.
Yeah.
I'm not having to handle those discussions and crazy working, so that's fun, yeah.
Yeah, very cool. Awesome. Well, this has been a lot of fun. I mean, you've certainly given us a lot of your time.
You're very welcome.
Yeah, sonic-pi.net. Go check it out. Video series. We'll have all the links in the description below for everyone to check out.
Can I mention one thing before you go?
Yeah, go
for it.
So
there's an artist called DJ Dave. She's in the States. You should definitely check her out if you want to see what people are doing with Sonic Pi. So we've talked a little bit about fun sounds and education, but actually she's an example of someone who's performing to huge crowds at massive venues where she's using Sonic Pi to live code the music and work like a DJ. And so if I go to a school now, I'll just play one of her videos, She's got a ton of really cool content to show what she's doing. And she really is an amazing example of the artistic potential that code and music in combination can enable. And I think is a really fabulous role model for if we think about what are role models for teaching computer science, are they Bill Gates or are they Jimi Hendrix? And of course, Jimi Hendrix wasn't a programmer, but if he was a programmer, he'd be my role models. Who are the Jimi Hendrix of programming? I want to find, and I think DJ Dave, she fits that bill really, really well. So definitely check her out.
I love that. DJ Dave, check her out. In fact, we'll also link her down in the description below. Thank you so much, Sam. It was really great to meet you. I appreciate you coming on. Everybody, please go check out Sam's stuff. Check out his GitHub. Check out the site. Sonic Pi looks really, really cool. Thanks again.